Hi everyone, and welcome to my presentation. My name is Gokhan, and I'm a postdoctoral researcher in the Intelligent Robotics Research Group at Aalto University. In this video, we are presenting our work on differential dynamic programming with nonlinear safety constraints under system uncertainties. In many real-world applications, robots are situated in uncertain environments with stochastic dynamics, where they are required to satisfy particular safety constraints, such as collision avoidance, or physical limits of their actuators. Within this context, safety can be defined as the feasibility and stability of a control policy that achieves the requirements of the desired task while satisfying the safety constraints, considering uncertainties affecting the system. In robotics, safety is an active research area and can be studied as trajectory optimization. Among the existing works, robust model predictive control methods are commonly used direct optimization approaches. However, they are generally over-conservative and computationally expensive. On the other hand, indirect methods, such as stochastic differential dynamic approach, are computationally efficient alternatives, but they either don't reflect the effect of additive uncertainties in control policy or do not include general nonlinear state constraints. Constraint version of deterministic DDP methods find some trajectories that pass very close to constraints, sometimes even tangentially, and creates a risk of constraint violation during operation. We propose a new safe trajectory optimization and control approach, Safe-CDDP, to address the question of how to handle nonlinear constraints and additive system uncertainties. Initially, we formulate a chance constraint optimal control problem as follows. To solve it, Safe-CDDP involves constraint tightening and constraint DDP modules that interact with each other iteratively. Due to its simplicity and fast convergence property, we employ an active set method for constraint DDP in this work. However, other constraint methods such as interior point and augmented Lagrangian methods can be also used in this framework. Let's start with an intuitive explanation of the constraint DDP algorithm. Let's assume that black dot represents a robot that tries to reach a green target while avoiding gray obstacles. We start with an initial feasible trajectory. DDP starts with a backward pass for a given trajectory and approximates action value function. This naturally leads to an affine controller that is computed by using Q derivatives. Next step propagates forward to get a new trajectory. Here, one can use the obtain affine control in the former step or solve a QP for input perturbation to ensure collision avoidance. Next, backward pass is applied to the new trajectory, and so on, until the algorithm converges. In order not to be overly conservative, constraint tightening converts the optimization problem into a deterministic one using locally optimal controls. This motivation is clear from the figure above that open-loop uncertainty propagation increases dramatically through the prediction. So first, we approximate the mean of the transition dynamics to the first order, employ locally optimal control, calculate the closed-loop uncertainty propagation, then the chance constraints can be modified for a given beta parameter as shown here, where the phi inverse is the quantile function of the standard normal distribution. As shown in this figure, selection of different beta values enables introducing different safety margins. Here, we evaluated Safe-CDDP for 3 robot dynamics in repeated simulations of 100 runs. Results show that Safe-CDDP can ensure completely safe trajectories for point and car-like robots and dramatically improve the collision avoidance for complex high-dimensional robots like Quadrator. This demonstrates that Safe-CDDP is a promising tool for complex and under-actuated robots in safety-required tasks. As an experimental setup, we employ Turtlebot 3 Waffle Pi that is a differential drive type mobile robot. We compiled CDDP and Safe-CDDP by deploying them on Raspberry Pi 4 Model B with 8 GB RAM. Turtlebot with Safe-CDDP was able to plan and successfully travel a safe trajectory to the goal position, avoiding the obstacles with reasonable safety margins, whereas CDDP results in trajectories that pass very close to obstacles and sometimes collide with one of them. Here we presented a new safe model predictive control approach, Safe-CDDP. It reduces over-conservatism using dynamic gains and ensures stochastic constraint satisfaction for robots in safety-required tasks. Moreover, Safe-CDDP can be easily adapted to a variety of CDDP methods and can be integrated as a part of a reinforcement learning algorithm to provide safety guarantees. Thank you. This work was financially supported by Academy of Finland.